Hello and welcome to video 3 on the Boolean Logic, Boolean Algebra and Circuits playlist. In this video, guys, we're going to be taking a sizable chunk out of the Boolean Algebra component of what you guys recognise as being Unit 8 in the classroom. Before we do that, however, I would really like you guys to be aware of the additional resources that are available for you on the course and which I've designed to help you build confidence tackling Boolean Algebra and Carnot maps. And the reason I've done that is because I know that this can be quite a challenging topic in terms of the amount of time that you need to invest practicing, and also because of the maths component as well. I'd like to spend a little bit of time putting the Boolean Algebra rules into context with a little bit of background information, and then of course we're going to explore and understand the 8 rules of Boolean Algebra as a precursor to using them to simplify Boolean expressions, and we'll be going through some worked examples in the next video. We're also going to explore Carnot maps a little bit later on in the classroom, because I do make reference to Carnot maps in these slides. We'll be tackling those a little bit later on, and of course in future videos on the playlist as well. So let's start off by having a look at the resources which are there for you. I may have mentioned these in the classroom, guys, but they will be certainly available in the resource area, which I've talked about and told you in the classroom where to find the resources associated with the course, the units, and of course with regard to Unit 8. You have the YouTube playlist, which of course you will know about because you're watching this video. There's a link below if you wanted to bookmark the link for the playlist in its entirety. In addition, the Boolean Algebra help sheet, if I haven't given you a copy of this yet in the classroom, it will be available in the resource area. I would suggest you pause the video and find yourself an electronic version to put up on the screen alongside this video, because I will be making reference to it and I will be going through the Boolean rules in a similar way that I've gone through them in the help sheet as well. Now, in addition, you will have past paper questions with worked examples, so there'll be a bumper pack of those available for you, and in addition a worksheet with additional example questions that require you to do simplification using Boolean Algebra. So you've got those sets of resources to help you right the way through this unit. Okay, let's make a start then and talk about the background for the rules of Boolean Algebra. Okay, so guys, on the screen you can see a screenshot from the OCR Specifications and Syllabus PDF, which covers A-level computer science. Now, as a related and very relevant aside, if you guys have not seen that and gone through it, please ask me about it in class. It is available for you, and I would really encourage you to read through the syllabus and specifications for the course that you're on for year 12 and 13, because I do make reference to it quite often on the course. Very useful, guys, for you to get a feel for what that document looks like. However, for the moment, let's just focus on what's relevant for Unit 8, and you can see that Part C, I have highlighted what we are covering in this video, and we have a little bit of a conundrum here, because it says using the following rules to derive or simplify statements in Boolean Algebra, and you can see that the minimum requirement for you guys is to learn 5 rules: De Morgan's, distribution, association, commutation, and double negation. Now that's fine, except for the fact that if you go on to the vast majority, if not all, websites and YouTube videos, they will extend the 5 rules to include an extra 3. So in other words, 8 rules to successfully tackle Boolean Algebra. Now let's have a look at an example of why I'm going to really annoy you guys with the idea that you need to learn an extra 3 rules which are not covered in the syllabus. So I know you're probably thinking this sounds really unfair because I've got 5 rules to learn and I'm being asked to engage with an extra 3 rules. So let me give you an analogy as to why I think it's really important to engage with all of the Boolean Algebra rules, not just the minimum spec in the syllabus, which is the 5 that you can see on the screen. Okay guys, so to demonstrate this, let me write down a trivial maths question for you. In fact, it's so trivial it's going to sound almost balmy. What is 3 minus 5? And instantly, guys, you will say it's -2. How did you know that? I suspect you guys did exactly the same as I do, which is to basically say, well, we're taking a larger number from a smaller number, so it's got to be a minus. Switch the numbers around. 5 minus 3 equals 2. We just need to make sure we put a minus sign on the end. Likewise, guys, with 6 minus 12, we're taking a larger number from a smaller number. It's got to be a negative. I just switch the numbers around, which is 6, and then make sure that I've got a minus on the front, because 12 minus 6 is 6. And then, of course, I need to negate the answer. I suspect you'd have done something very similar, even if you would articulate it slightly differently. Now, let's imagine that you were a much younger student and you didn't know about this type of thinking and this little trick where you switch the numbers around and put a minus sign on the front. How might you derive the same answer? Well, you might do what year 4, 5 and 6 students always do in maths lessons, I think, which is to draw a number line. So let's draw a number line. In fact, let's make my number line look reasonably straight. There we go. So let's put 0, 1, 2 and 3. I know this sounds crazy, guys, bear with me. -1, -2 and -3. So if we had the sum 3 minus 5, I would start off at +3 and I'd count backwards 5 times. 1, 2, 3, 4, 5, which gives me -2. That might be the way of working this out if I didn't know this handy little trick of switching the numbers around and just putting a minus sign on the front. Okay, so the reason I've suggested that you watch this really trivial example of maths is to make the point, actually, that with those extra 3 rules, you're getting an opportunity to learn a trick of the trade, just like we did with swapping the numbers around and putting a minus at the front, rather than deriving the answer the long way. And in an exam, if you've got an opportunity to know a little trick, okay, you can call it a rule or a theorem if you like, it's a little trick of the trade which enables you to get to the answer quite quickly. You really don't want to be deriving the answer separately without knowing this little trick. Okay, so it's the best analogy that I could come up with to explain why it is that I'm asking you guys to engage with an extra 3 rules, is to give you an opportunity in the exam to take these very powerful shortcuts. Of course, it also means that you're less likely to make an error. So for example, if I counted back too far on my number line, okay, I might end up with the wrong result. Getting straight from the question to a solution with these little tricks, guys, is very, very powerful, and it's going to save you time and effort in an exam. Okay, whereas if you didn't know these little tricks, you'd have to derive the answer on the fly in an exam. So on the slide in front of you, you can see the 8 rules that I'm asking you guys to become aware of, then to learn, and then to practice. And I've put red boxes around the 3 additional rules which are over and above the minimum learning spec, if that's the right phrase, that we've got in the OCR PDF. So we start off with the general AND rules and the general OR rules. These are very, very useful rules to know in advance before you walk into an exam. They will save you having to rely on having a picture in your head of the OR and AND truth tables, because if you don't know these rules, you'll have to draw those tables on a piece of paper and then look for opportunities to apply AND and OR logic. Know these rules in advance and you won't be disadvantaged in an exam, taking more time to get to the end solution. The other rule to draw your attention to down here is the absorption rule. If you look on the spec, you can see that the distribution rule is part of the minimum spec, but in addition, the absorption rule is a special case of the distribution rule. But it's very useful to remember that in the exam, because it means that you won't have to derive it or spend longer than is needed getting to the same solution by using the basic distribution rule. So if you've looked on the help sheet, you'll see that I've highlighted 3 of the rules in green, and I've done the same thing on the slide here. And the reason I've done that is because I think out of all of the 8 rules, these are the 3 rules which become the easiest to remember, to apply, and they become intuitive and second nature. And the reason for that is because they are very similar to basic algebra rules that you guys have been using in maths, in some cases since year 7. So once you become aware of these rules and what they're actually saying, they become second nature very, very quickly, because you've been doing something similar in maths for many, many years. Now, De Morgan's laws, they are called laws. There's 2 of these to remember. They're very, very similar. Although they're called laws, we apply these in exactly the same way as the rest of our rules. So De Morgan's laws, will come across these a little bit later in the video, obviously, but again, if you know these laws, it's very, very easy to spot opportunities to apply them straight away when you're given a Boolean expression to evaluate. So in the next part of the video, we're going to be focusing on 2 out of the 3 additional sets of rules which you guys need to know for your exam. In this case, it's the general AND rules and the general OR rules. In the course of doing that, we're going to look very briefly at how those rules are derived, and I'm also going to give you some suggestions about making it easier to learn those additional sets of rules. So we'll see you in the next part of the video. Okay, so let's have a look at our general OR rules. There are 4 of these. I'm going to write them down in exactly the same format as you will see them expressed on the internet and in textbooks and in YouTube videos as well. So I'll just write these down and then I'll explain where these come from in a second. So we start off with A. ORed with 0 is logically equivalent to A. A ORed with 1 is always logically equivalent to 1. A ORed with A is always logically equivalent to A. And lastly, A ORed with not A is always logically equivalent to 1. So where do these rules come from? Well, the best way to demonstrate where these rules come from is to actually draw a truth table. This is why they're called truth tables, because the truth tables give us a fundamental truth or sets of truths which are essentially expressed in our 4 rules here. So let's see how this works. I'm going to draw my truth table. Not quite sure what happened there. Never mind. Serves the same purpose. Let's divvy this up. At the top, guys, let's use a different colour. We've got A, B and Q. Let's write down our combinations of 0 and 1. We've got 0, 0, 0, 1, 1, 0, 1, 1. And we know, guys, with an OR gate that the only time we will get a 0 is when A and B are 0. On all other combinations of A and B, we will get a 1 on the output. So what these rules are basically saying is, if we're not too fussed about whether A is a 0 and a 1, but we're looking at specific values of B, can we establish a relationship between Q and the original value of A? This is what we're basically saying. So let's see how this works. We're looking first of all here at A ORed with 0. So let's have a look at all cases where A, doesn't matter whether it's a 0 or 1, is ORed with a value of 0. 0 is going to be essentially in our B column here. So let's have a look where A is 0 and B is 0, which is there, and then A is 1 and B is 0, which is there. We're not interested in any other combination from B because we've set this to 0. So if we have a look at these 2 instances, you can see that the value of Q on the output is essentially always the same as our input of A. So we have a fundamental truth being represented here, which is basically when we take a value of A, whether it's 0 or 1, and we OR that with 0, on the output, if we illustrated this as a logic gate, we would always get on the output exactly the same value as we had for A on the input. In other words, A ORed with 0 will always give us is logically equivalent to the input A. Let's have another look at one of these. I'm going to leave the other 2 for you guys to do yourself, just to verify that these truths are true. Let's have a look at this bottom one. We're saying that A or not A is logically equivalent to 1. That means if A is 0 and 1, and this column here is the opposite, the negative of A, in other words B is not A, are we going to get 1 on the output? Well, let's have a look when that's the case. We've got 2 instances here where we have A and B as opposites. If you look at 1, okay, in both cases Q always gives us a 1 on the output. So a fundamental truth here, which we need to reflect in our rule, is when A is ORed with not A, we will always get as an output, if we illustrated this as a logic gate, of 1. So we can say that A or not A is logically equivalent to 1. Okay guys, so let's go through exactly the same process with the AND rules. Let's write these down first of all in the format that they're normally expressed. So we will have A and 0 is logically equivalent to 0. A and 1 is logically equivalent to A. A and A is always logically equivalent to A, and lastly A and not A is always logically equivalent to 0. Okay, let's express these as a truth table where we get our fundamental truths from, which are expressed in these rules. Let's do the same as we did before. Done a slightly better job of creating what looks like a reasonable table here, I think. Let's do these up as usual. Okay, let's pick another colour for A, B and Q. A, B and Q. So just like we did before, guys, we're saying that if we express our Boolean logic and we illustrate that using a truth table, then we can talk about this in terms of inputs and outputs, just as we did before. Let me just twist this around a little bit. There we go. So 0, 0, 0, 1, 1, 0, 1, 1. And of course with an AND gate, let's just write that up here. With an AND gate, we are only ever going to get 1 here. All other combinations of 0 and 1 that aren't both 1 will give us a 0. So let's go through the same type of logical thinking that we did before. With this top one, A can be 0 and 1, but we're fixing B, or we're just looking at B when it has an input of 0. Here's B when it has an input of 0. A, of course, we're expecting 2 occasions, one for A equals 0 and one for A equals 1. In both cases, the output Q is always 0. So this is a fundamental truth. When B is 0, it doesn't matter what A is, we will always get a value of Q on the outputs. So this is true. Let's look at one other, and I'll leave you guys just, as I said before, to have a go at verifying these for yourself. Let's look at this one this time. When A and A, okay, in this expression, A and A should give us the logical equivalent, or be logically equivalent to A. Let's see if that's the case. That's basically saying what do we get for an output if both B and A are the same. So let's have a look at all instances where B and A are the same as inputs. We've got one here where A is 0 and B is 0. We've got one here when A is 1 and B is 1. In this case, we can see that output 0 is the same as the A inputs of 0, and in this case the output of 1 is also the same as A of a value of 1. So we have a fundamental truth represented here as well, which is essentially saying if we have a AND gate, okay, and both of our inputs are a value A, then we will get exactly the same on the output as our input value of A. And you can see that here just by looking and analysing the truth table. Okay guys, so in the corner of the board I've written down the 8 rules, okay, 4 for the OR group and 4 for the AND group. Now I know you're looking at these going, well, I'm expected to learn, you're expecting me to learn 8 separate rules, all of which look the same, and if I manage to remember them at all, I'm likely to get them mixed up and confused. So actually, to help, I didn't, well, I hope it helps, I didn't learn when I was a student the OR and AND rules as 8 separate rules. I actually learned them as combinations. So for the OR, I learnt them actually in the same format that I put down in the help sheet. So these were combined together. So we have A or A is logically equivalent to A, or 0 logically equivalent to A. And then this bottom set of 2, wrap it up into one expression by saying A or not A, logically equivalent to A, or 1 logically equivalent to 1. Now I'm not going to demonstrate that these are correct, because if you look here you can see the logic says that if A or A equals A there, and A or 0 equals A, then logically these 2 expressions here must also be the same. Hence we wrap them up into 2 single expressions. So if you're looking at this, because this is all that I learnt when I learnt these groups, and you're looking at that and you're thinking, how on earth does that help? What I did actually was I separated out the changeables. So we've got A here, 0 gives us A, and then the bottom one we've got not A, and 1 gives us 1. And I learnt this a bit like a phone number. So if you look at these 6 characters, you've got A, O, A, not A, 1, 1. And I actually learnt these like a phone number. So A0A, not A, 1, 1. A0A, not A, 1, 1. That was my telephone number for the OR group. And then in an exam I could just write these down very quickly on a piece of paper. A, 0, A. So we've got A or 0 equals A, that's that bit. and then we've got A or not A or 1 gives us 1. Right, so that was the way that I learnt these, and likewise if we do the same thing for the groups of ands at the bottom, we've got A, and A is logically equivalent to A, and 1 is logically equivalent to A. That's our first set. And then A and not A, logically equivalent to A, and 0, logically equivalent to 0. So that's my group of 2 expressions for the AND logic, and do exactly the same thing. So my telephone number to remember for AND is A1A, which is A1A, and then not A 0 0, not A 0 0. So these are my 2 telephone numbers that I learned off by heart to represent these 2 groups. So rather than learning 8 separate rules, I learnt 2 telephone number equivalents, each containing 6 digits. A0 not A, A11, A1A not A 0 0. Right, considerably easier than learning 8 separate rules, and as long as you remember your 2 telephone numbers, you can actually backtrack and recreate the rules just knowing these 6 digits for each. So hopefully, I mean, you guys decide, hopefully that might be an easier way than learning your 8 rules, or you might just decide to learn the 8 rules, but that gives you an alternative. And I've put these combined expressions, 2 for each, in the help sheet. So if I just show the help sheet, guys, here, right, you can see here that I've expressed them in these joined up expressions on the left hand side here, and I've actually put the tables in as well, so you can validate that all of these are fundamental truths. Okay guys, so in this part of the video we're looking at De Morgan's laws. We've got 2 laws to consider. Rightly or wrongly, I tend to consider De Morgan's laws as being a single rule, because the process that we follow for each is in fact exactly the same. So let me write these down and explain what's happening. I'm going to use exactly the same example that I did in the help sheet. So essentially De Morgan's laws says that when we have a negative of A and B in brackets, this is logically equivalent to negative A or negative B. So what's actually happened here is that we've taken a term outside the bracket, we've applied this term to both of the variables in the bracket, hence negative A and negative B, but we must remember to swap or flip the operator. This is really, really crucial, and it won't be the first law that we come across, or the first rule that we come across, where we need to flip or swap the operator as part of our final expression. So A and B all knotted, if that's the right expression, is logically equivalent to not A or not B. Now the second rule is almost exactly the same as the first one, except that we're looking at the other operator. So in this case, A or B is logically equivalent to not A, and then we have not B again, because we've applied our term outside the bracket to each of our variables inside the bracket. We've got rid of the brackets, but we must make sure we swap or flip our operator. So this time we're going to swap it from an or to an and then we can say that A or B, all negated or all knotted, is logically equivalent to not A and not B. And that is essentially our 2 De Morgan's laws, De Morgan's law 1 and 2, which you could consider to be a single rule. And as long as you follow the same process, you can apply this in exactly the same way. You just need to make sure that you flip the operator in both cases. So let's go through the inversion, or sometimes called the double negation rule. And if you remember from earlier on in the video, I suggested that this was one of the rules which we could flag as a green, because potentially it becomes intuitive and easy to remember and to learn. Why is that? Well, let's have a look at an example of maths that you guys have been doing for a long time by writing down the expression minus 3. And if I said to you guys, what is that identical to, straight away you'd say, well, you cancel the 2 negatives out, it essentially becomes plus 3. And of course we don't normally write down the plus, so it's just 3 on its own in this case. Likewise, if I had a more complex expression, let's say minus 2 multiplied by minus 3x plus 1, what is that equivalent to, well, we take the term outside the brackets, we apply it to each of the terms inside the brackets. So of course we have 6x with these two, negative and negative gives us a plus, so it's 6s, and then minus 2 multiplied by 1 of course gives us minus 2. So that's our expression with the brackets removed, having taken the term outside the bracket and applied it to the terms inside the bracket, which leads me on very nicely to the example which I've given you in the help sheet. Because in the help sheet what I've done is I've given you a very basic example. You can see here I flagged it as green as well, as easier to learn. Here's a really trivial example of where negative a cancel the two negatives out to give a, but it is very often the case that you will be using double negative in the context, or double negation in the context of one of the other rules that you are actually working with. It's actually quite important not to get put off or to have these rules disguised because you've got additional negatives that are appearing in brackets. And so I'll give you an example of what that means here with this particular example that I've popped in the help sheet. So what we have in the help sheet is we have an example. Let's say that we are asked to simplify this Boolean expression, and the expression that I've given you is negative, and then we have negative a, okay, and then we have or negative b. All right, and we want to find a way to simplify this. And essentially what you've got here, if I put my two fingers over the negative inside the brackets, you can see that straight away this is an opportunity to use De Morgan's law, because we have a negative outside the brackets and then we have two expressions inside the bracket. It's just that we've got these two negatives here which sort of disguise the fact potentially that this is an opportunity for De Morgan's law. We actually apply De Morgan's laws, or the rules associated with De Morgan's laws, in exactly the same way that we would normally do. So we take the term outside the bracket and we apply it to each of the terms inside the bracket. That essentially gives us negative a, because we've already got a negative in here, we've got a negative outside as well. Flip the sign, don't forget to do that, and then we have negative b. Okay, now of course now we've got that, we can simplify it even further by cancelling out our two negatives, and we simply are left with a and b. So this expression here can be simplified to simply a and b, and that's because in looking for De Morgan's, an opportunity to apply De Morgan's laws, I've not been put off by the fact that we've got these negatives inside the bracket. Okay, so let's have a look at the association rule, and again this is one of the ones which I've highlighted in green, both at the earlier part of the video but also in the help sheet as well. Here it is, the association rule, an easier to learn rule. So let's give an example of why this becomes intuitive to use, and bear with me on this because this is going to sound so trivial that you're going to wonder why it's actually a rule at all, and I'll explain a little bit more about that later. So if I gave you this expression, for example, 1 plus 2 plus 3, that's easy to evaluate. This is also identical to this, 1 plus 2 plus 3, okay, and that is also identical to 1 plus 2 plus 3. Now you guys intuitively know that in essence in this particular context these brackets are redundant, and the reason for that is because we have the same operator in our expression. Okay, so 1 plus 2 plus 3, because we've got the same operator and we're essentially performing the same mathematical routine for each of our numbers here, it doesn't matter where we put these brackets. And the same applies in Boolean logic, and we call it the association rule. So I can express that by saying, in a very similar format actually, and it's in the help sheet, is if I have something like A and B and C, that is identical to, or logically equivalent to, A and B and C in brackets, okay, which is logically identical to A and B and C. Okay, so you're probably thinking, right, this is so obvious, why is it actually a rule at all? And the reason actually for this, and it's going to be something that we'll look at in some of the worked examples in the next video, is that In most cases, of course, you would treat these brackets as being redundant, but there are instances, and I'll just write this down very quickly, there are instances where if you have something as part of a bigger expression, if you do have a, let's say, or, because the same thing applies with or as it does with and, A or B or C, or C, there might be, as part of the expression that comes next in the Boolean algebra that you're applying, there may actually be something in here where you do actually want to deliberately put two of your terms in brackets so that you can use this thing here in the rest of your expression to then apply to these two in brackets. And actually, in strangely enough, in Boolean algebra, it's quite useful to remove brackets, but there also are occasions where we deliberately want to introduce brackets, which you guys would have considered to be redundant a little bit earlier on, simply so that we can create the equivalent of one of our rules where we do have brackets that we want to exploit. So actually introducing brackets so that we are creating an opportunity to use one of our 8 rules, Boolean algebra rules, is something which crops up quite often, and this is an example, or will be an example, that we'll cover in the next video. So guys, let's have a look at the commutation rule, and the example that I've given in the help sheet are examples such as this. We can say that A and B and C is logically equivalent to C and B, and A is logically equivalent to B and A and C. In other words, it doesn't matter which way around you put these terms. Again, this works because we're applying the same mathematical mechanic. We've got the same operators here. So just like, guys, we would say, for example, 2 times 3 times 4 gives us exactly the same result as 4 times 3 times 2. As long as we've got the same operator and we're doing the same mathematical routine with our numbers, we can move our numbers around and it doesn't make any difference to the logic, or in this case, our final calculation. And again, if you're wondering why, exactly the same reason that I went through in the previous part of the video with the association rule. This is so that we can manipulate our expression in order to exploit some of the rules that we have at our disposal with our Boolean algebra. And again, more on opportunities to use association or commutation rules when we do some of our worked examples. Okay guys, so that leaves us with 2 rules to go, the distribution rule and the absorption rule. And if you remember what I was saying earlier in the video, the absorption rule, which we'll look at next, is a special type of distribution rule. So we'll look at the distribution rule first. I think actually, you might disagree a little bit later on when you've had a go at this, but I think that the distribution rule tends to be the one where students, not just students, actually the rest of us as well, when we're doing Boolean algebra, it's the easiest rule to apply and to make errors in the process, because it can actually get quite complicated applying the distribution rule. We'll look at examples obviously in the next video, but this isn't entirely alien for you, because this is the equivalent of factoring out and factorizing, or finding the factors of an expression or variables, is something which you guys have been doing in maths, particularly at GCSE. And the example, the best analogy, the best alternative maths example that I could come up with is the one that I put in the help sheet. And the one in the help sheet basically says we have, if we have something like z, okay, and then 3y, hang on, I've just lost my place, 3y, yeah, plus 2. Okay, we could factor this out. All right, so we end up with 2 sets of brackets. So we're going to apply z to each of the variables, each of the terms in the brackets. We're going to end up with 2 sets of brackets. Okay, and let's do the first one first. So z, okay, multiplied by 3y, okay, that becomes z multiplied by 3y plus, okay, because that's our term inside the bracket, becomes our term outside our pair of brackets. And then we do the same again with our 2. Z multiplied by 2 is simply 2z. Okay. Now we could actually call that 3yz or 3zy if we wanted to, but we've got the gist here, right? This expression here is identical to this expression here. Now I'm not sure whether the term simplifying is the right one, because this doesn't look simpler than this one. I think to factor out is probably the correct expression. If you're looking at this and saying, hang on a minute, why would we want to go from one set of brackets to two sets of brackets? Okay, I will explain that in the context of the Boolean algebra example that we're going to look at in a second. So let's just get rid of this one and let's have a look at the example that I did in the help sheet. Now this is an example where, with the distribution rule, it's one of those examples where we can't use the rule unless the operators that we're working with are opposites, and I will show you what I mean by that in a second. So let's write down the example that we've got in the help sheets. We have A, and then we have and then we've got B or C. Okay, and we're looking to create an alternative expression where essentially we're going to have two sets of brackets, just like we saw with the maths example a little bit earlier. Now the distribution rule only works if this symbol here, let me find a pen that actually works now, this operator here, okay, is opposite to this operator here. If they are the same, we don't actually need the distribution rule, because if we had A and B and C, in other words the same operator, that's essentially what we were talking about earlier. This is an example of the association rule. I can actually remove the brackets and it's just A or B or C, so there's no need to have an extra rule to apply to this. So the distribution rule is only valid if our two symbols here are opposite, so you need to be really careful to check that out. Okay, it could be either way around, doesn't really matter. So if I just rub this out and just put my symbols back, my operators the way that they were. Okay, so we've got A and B or C. Okay, so we're going to apply exactly the same logic with this as we did with our maths example with the z's and y's. We're going to take each of our terms in turn. We're going to end up with A and B in here, and then A and C in here. Okay, this is the operator that we want A to apply to B and C, so we're going to have and in here, and then the one in the center of the brackets, of course, is going to be the or, because that's what distinguishes the B and the C, the two sides of our operator there. Okay, so this is what you get with the distribution rule. We've taken this expression here, A and then B or C in brackets. We've factored it out so that we've got A and B or A and C. Why on earth would you want to create two sets of brackets then when we just started off with one? You will see why we do this in worked examples. Let me just see if I can move this over a bit, guys, because we've gone off the edge a little bit. There we go. Ooh. There we go. That's better. Yeah, you will see why in the worked examples, because we will be very keen, as one of our techniques for doing Boolean algebra, to identify expressions on either side of OR operations like this. Alright, and when we can do that, so we're a little bit limited here, okay, but these are nice, neat expressions which we've created on either side of an OR operator, and once we've done that, we can take each of these operations, these expressions in turn, and work with them separately, and that's actually very nice. It's a very encouraging thing to be able to do that, and we'll see examples of this both with Boolean algebra but also with Carnot maps as well, when we are looking at separate expressions separated by a common operator. Okay, so that leaves us with the absorption rule, okay, which is basically a special type of distribution rule. And in fact, what I'm going to do to show you the absorption rule is they are so similar. In fact, I'm just going to rub out distribution here and I'm just going to write down absorption, okay, because I'm going to keep this format here basically the same. So let me just write down absorption. Okay, now the absorption rule is exactly the same, well, okay, well, almost exactly the same as the distribution rule, except that if we have a term on the outside which is the same as a term on the inside, this then becomes a special case of the distribution rule. So for example, if this, let me just change B and turn it into A. Okay, so it's still an example of the distribution rule, but now because we have two common terms, one on the outside and one on the inside, if we actually use the distribution rule to evaluate this fully, okay, you would find that actually this example of the distribution rule, this special one with the two identical terms, is actually equivalent to A. And in fact it is exactly the same as if we've swapped these two around. If we had A or A and C, all right, exactly the same format except that I've changed the operators around, that also is logically identical to A. The rule with the absorption rule is that we have to have a duplicate variable. We have to have a variable outside the bracket which matches the same variable inside the bracket. Where we've got a match, in this case A and A, then it becomes logically identical to that duplicate variable. So let me just give you another example where we could apply the special absorption rule version of the distribution rule. So if I had, for example, C and then A or C, okay, this is our term that's both outside and inside the bracket, so it is logically equivalent to simply C. Likewise, if I had C or A and C, exactly the same, again, doesn't matter, as long as these operators are the opposite way around, they're opposite in each of our examples. We take the variable that's common to both here, outside and inside the bracket, and it becomes logically equivalent to that duplicate variable, okay, which is C. So this is the absorption rule. Very, very useful to remember this, because if you spot this, okay, in your Boolean expression, immediately you can essentially cross these out and simplify this radically just down to the single C, and this expression disappears completely from your example that you need to use Boolean algebra for. So it's very, very useful to know this and spot it straight away as part of your working out. Okay, so we've been through all of the 8 rules. Let's pop back to the original slide that we had at the outset of the video. The objectives of the video really were for you guys to be aware of the additional resources available for you, to put the rules of Boolean algebra into a bit of context, a little bit of extra background, and of course we did that by looking at the 5 minimum requirements on the OCR Spec, and to explore and understand the 8 rules of Boolean algebra as a precursor to using them to simplify Boolean expressions, which is what we're going to do in the next video. So I hope you found this video useful as a supplement to your classroom learning, and I will see you in the next video on the playlist.